All right. Let me just double check if, okay, this is fine. So here is where we stopped in the last class. We basically just looked at this slide about compensated semiconductor, and then we stopped because we ran out of time. So we will start here. And I think this is a really nice place to start because this will help us review all of the concepts that we learned in the last class. So I'll go back to the drawing board first. Let's work on it together, okay? Please respond because, this is face-to-face now. It's much better. Let's start with drawing the conduction band and valence band. It's as if you can visualize the material now in front of you. This is how it should be, right? You should be able to describe the properties of a material looking at the band diagram. And whatever you're describing, you should also be able to reflect that in the band diagram. This is the utmost target from these lectures. So when I say conduction band and valence band, if it is an intrinsic semiconductor, where should be the Fermi level for intrinsic semiconductor? Please respond. Thank you. Somebody said it. But, please speak up. Everybody should respond. So this is exactly in the middle. Intrinsic Fermi level. Okay, you may not try to answer now, but when you'll be, in front of your employer, potential employer, and trying to go for an interview, you have to answer, right? If you just stay silent, you're not going to get the job. And if you make a mistake now, nobody's going to judge you, right? That's the best part. You are with your buddies. So, I mean, what's the worst that could happen? But there, you'll not be with your buddies. You'll be with the buddies of your boss, like future boss. So it's a different setting. So please go ahead, answer, and make mistakes. It's okay. And ask questions. Remember, no question is a silly question. You could ask anything, and not necessarily related to the things that I'm teaching you. You could, if you have a question in your mind, go ahead and ask me. It's okay. All right. Intrinsic Fermi level. So if I tell you that this is a semiconductor, say silicon, and I doped it with N-type dopant, okay, N-type. That means you have, and we'll be using these terms interchangeably. N-type dopant or donors. I dope it with donor atoms. Means the same thing, okay? So where should be our new Fermi level now? Now it's no longer intrinsic semiconductor. We should call it extrinsic semiconductor. Well, it's like linguistic. Extrinsic semiconductor. Now, where should I draw the new Fermi level? Thank you. Yes, yes. So it should be above the intrinsic Fermi level. This is EF, N-type doped. Now, if I tell you that, okay, I've doped it with N-type dopant, but I've doped it more than I did last time. If I dope it more than I did it last time, what will happen to the Fermi level now? Will it go closer to the conduction band or farther away from the conduction band? If I dope it heavier, like with heavier dose, what will happen? Yeah, I mean, don't hesitate. You can be wrong, but be wrong in a confident way. Like, yeah, this is what I think. Okay, go ahead and tell me. It's okay. Remember, confidence is like 50% of the job. Yes, thank you. And I appreciate the confidence. Thank you. Yes, it could be close. It will be closer if you dope it heavily. And this is, okay, so heavily doped N-type. But I mean, heavily doped is a relative term, right? How heavy are we talking about? Heavier than what we used to have in the green situation. Now, if you keep doping it with more and more donors, right, N-type dopant, there will be a situation where, and we discussed this in the last class, degenerate and non-degenerate semiconductor, right? Degenerate semiconductor. So apparently, we are assuming that the donors or the dopant atoms, they're basically just impurities. They're just there with silicon, here and there. But if you dope it so heavily, they will, at some point, they will start interacting with each other like the host atoms do, by the way. Remember, the host atoms or silicon, they interact with each other. And I'm basically taking a step back here. In a silicon crystal, silicon atoms interact with each other. And that gives rise to these band diagrams, right? The bands exist because of the interaction between silicon atoms in the crystal. Otherwise, there would be no concept of band at all, right? Remember, that's how we started. But now, when the dopant atoms start interacting with each other, they have their own bands now. that becomes a little bit more complicated, but you don't necessarily need to visualize it to be that complicated. You could just represent that using the new position of Fermi level. Okay, so when you have a degenerate semiconductor, so it's so heavily doped that the Fermi level basically goes up inside the conduction band. So basically this is the Fermi level. Now when you have an N++, so typically with N plus, I mean, doesn't matter, plus 2 plus or 1 plus, if you use a plus, that typically represents it's heavily doped, so heavily doped that it's basically within the conduction band now. Some people, now if I go even higher up, it could be N++, and so on. So these are all subjective, by the way. Okay, now erasing all of this because that was getting busy. ECE, EV, my Fermi level, if my Fermi level is here, this is degenerate semiconductor. If my Fermi level is closer to conduction band, but under the conduction band, it's non-degenerate semiconductor. Okay, and we talked about all of this. What will happen to the valence band? P-type. This is all N-type now. And I told you whatever you do for the N-type, you could easily invert it and get the P-type. Let's do that quickly, just as a review of what we learned. So for P-type semiconductor, the Fermi level will be close to the valence band for conventional P-type or non-degenerate P-type. Okay, but if you heavily dope it, then the Fermi level will be below the valence band for P plus or P plus plus, doesn't matter. The heavier the doping is, the deeper the Fermi level will go in valence band. Any problems so far, folks? Are we all good? Okay, so now with that understanding in mind, I know this is a busy figure, but follow along and hopefully we'll just break it down into small things that we already know, and it will be easier for us to debug. And trust me, get into this habit of debugging a complicated diagram into smaller things, and things will start making sense to you. And the deeper we go in the course, the more complicated figures will come up, and that's okay. We'll be able to handle it. So let's see. Let's start with the easiest of everything: conduction band and valence band, EC and EV. And I'll explain what compensated semiconductor means. In practice, you don't just typically have N-type dopant or P-type dopant in a semiconductor. It's very difficult to do so. And the reason for that will be clear, hopefully, towards the end of this course. When we talk about MOSFET, maybe somewhere in the middle as well, we'll talk about BJT, and I'll show you how we actually make the devices in semiconductor foundry. And considering the practicality, we have to use both type of dopants in any semiconductor. Even if it is a P-type, we have N-type dopant as well. If it is an N-type, we have P-type dopant as well, vice versa, right? So considering that in mind, compensated semiconductor is a more realistic version of semiconductor. Basically, we don't really have N-type or just P-type, okay? So compensated means you have both type of dopants, but one overcomes the other, and that becomes the prevalent one. Okay, so if you have more N-type than P-type dopant, eventually the semiconductor will be N-type. But it's a compensated N-type. That means there will be holes and electrons, but probably there will be more electrons than holes or more holes than electrons in the semiconductor, compensated semiconductor. And here is how the dynamics works. Let me explain. So we know conduction band is valence band, and we have the intrinsic Fermi level right in the middle. Okay. Now let's use a different color here. So if I say I use an N-type dopant here, just N-type, don't worry about degenerate, okay? Just conventional N-type. So that means the Fermi level for that donor, the donor energy level per se, will be here. This is the donor level. Does that make sense? So when you dope with N-type, the donor creates a new energy level, which is closer to the conduction band. And by the way, we just use that level to be the new Fermi level anyways. Because if the electrons are up to this point, that means the Fermi level is now there. Does that make sense? For the sake of this argument, let's not talk about Fermi level for now. I'll talk about Fermi level later on. Remember, intrinsic Fermi level is no longer applicable for this material because you're doping it. We just draw it as a reference, point of reference. If it were intrinsic, no dopant, then the Fermi level will be exactly in the middle, say. But just as a frame of reference, nothing else. But this is a real energy level that the donor creates. And this is a real energy level that the acceptor creates. So the acceptor will create an energy level closer to the valence band and encourage the electrons in the valence band. Maybe, I mean, if you have some more energy, it could come here, right? I mean, the acceptor cannot deal with the conduction band directly because it's too far, but it can interact with the valence band easily because it's close by. That's what the trick is. So you have a energy level created by the acceptor, you have an energy level created by the donor. Okay, now what? Let's see. When you have donor, which can donate electrons, it will donate electron easily, driven by thermal stimuli, and it will create additional donor electrons to the conduction band. See, we are covering aspects of the image already. At some point, everything will be taken care of. And what happens to the acceptor? The acceptor has less electrons than its neighbors. Okay. Do you remember this? It doesn't really have less electron. It only has less electron when it notices everyone else around me has 4 electrons, like silicon, right? And this is a trivalent element, like we talk about. 3 electrons in the outermost shell. Typically, that's what it has all the time. But when it comes in an assembly where everyone else is silicon, it feels they all have 4 electrons. I need 1 more. So that's why there is a lack of electron, but it doesn't really represent a lack of electron. But still, it's all relative. So what it will do is it will take some electrons from the valence band. And I told you already, just to repeat the same discussion, we don't typically represent it as taking electron. We represent it in a way that this level is giving hole to the valence band. That makes it easier for us to visualize. So it gives holes or creates holes to the valence band, and holes could be like positive charge particle, visualized as positive charge particles. But deeper down, it's all electrons, by the way. Okay. All right. So you now understand. Oh, by the way, these are acceptor holes, basically holes coming out of the acceptors. That's how it's represented. So we covered all this. Now, when this donors give up electrons, meaning give up in a way that it's letting the electrons go and conduct around the material. That means it's no longer bound within the material itself, within the donors. It's no longer bound within the donor. Maybe the donor was arsenic, it had 5 electrons around it. It gave up 1 electron. Just go. I don't care about you. Just go and conduct. So now, all on a sudden, it has 4 electrons, which is not natural state for arsenic. So it's now charged. It's now an ion. It has given up an electron. And it will be, when you give up an electron, you become a positive ion. So these positive charges are stationary. Remember, there is a difference between this positive charge and the other positive charge. These positive charges are stationary because their ions are stuck in crystal. But the other positive charges that you see here, they're not stationary. They can move around. Why? Remember, we talked about it. They are holes. So some other electrons will come and nullify this hole, but create a hole somewhere else, right? That's how indirectly they lead to conduction. But they can change. But these ions typically never conduct, where they're stuck. So there is a difference. Remember, this semiconductor is basically like a melting pot of different kind of charges. Some stationary, some mobile. We care the most about mobile charges because they participate in conduction. They can be manipulated, they can be controlled. But the stationary charges, don't ignore them. I'm highlighting this. This diagram is in the textbook, by the way. There is a reason why we talk about all these stationary charges, despite them being stationary, because they have a huge role to play when we start designing devices. They create, how many of you have heard about diode? PN junction diode. You have all heard about diode, right? Taken electronics 1 and 2. So you know the diode has a turn on voltage. It takes some minimum voltage for you to turn on the diode, and then it goes into action. So for example, these stationary charges determine how much turn on voltage will a diode require, for example, just as a very simple example of how they can show up in characteristics. So they're not doing much in terms of carrying current, but they have other roles to play. Nothing that you see in this diagram is useless because there are many other components that we're ignoring. We're only showing you the ones that will be necessary for your device level understanding. All right, so we know that some charges are stationary. So these are positive charges that are stationary. Similarly, using the opposite argument, these are negative charges that are stationary. So you have stationary positive and stationary negative charges. Okay. Now, these are negative charges that are basically electrons. They can participate in conduction. These are holes, which are pseudo positive charges. They can also participate in conduction. What else? Let's see here in this region. This is basically reminiscent of what happened in an intrinsic semiconductor. Even if you didn't have any doping at all, the semiconductor itself was taking some energy from the environment, KT over Q, as we talked about, and then it's exciting some electrons all the way from valence band to conduction band. This is difficult to achieve, but it still can be done. That's why, I mean, it's not drawn to scale, obviously, but you see the numbers of such electrons is lower, just to represent that they are actually lower in number, but there will be some. But what is the signature of this situation? They are created in pairs, by the way. So you can create more electrons. So you can create 100 electrons and 50 holes. Who will determine the number of electrons here? Can you tell me? Who will determine the number of electrons? Number of donor electrons. These dopant, these donor atoms, these n-type dopant atoms, they will determine. The more n-type doping you use, the more electrons will be created as donors, donor electrons. Does that make sense? Does it have any link with what happens here? Will they be created in pairs? No. These will be created in pairs. Notice. These will be created in pairs, meaning one positive charge that is stuck, one negative charge that is free. So you're creating more and more negative free charges. Not any representative positive charges. Making sense? The positive charges are stuck. They're not moving around. So if I need to create 1000 free electrons in a way that they could flow around, I could dope it with 1000 in theory, 1000 donor atoms, and there you go. You created 1000 electrons. And none of them will lead to any holes. But I can, if you need to create, say, 20 holes somehow, how can you do it? You use 20 acceptor atoms, and they will interact with the valence band and create holes in the valence band. So you see, these are independent of each other. They can be created like irrespective to each other, basically. You create these electrons with the donor level, you create these holes with acceptor level. Does that make sense so far, folks? Any problem? And by the way, what I'm telling you, I'll change that narrative slightly towards the end of this slide. But bear with me until then. As of now, based on our understanding so far, these electrons can be arbitrarily controlled by the donor level. These number of holes can be arbitrarily controlled with the acceptor level. They don't have like matched creation or something like that. But here, in the thermal case, they're created in pairs all the time. So one electron goes to the conduction band, leaving behind a hole in the valence band. So they're always in pairs. If there are 50 thermal electrons, there will be 50 thermal holes. There is a difference, you see, in the process. Okay. But once they are there, doesn't matter where they came from. They are all electrons. Oh, they're all free electrons. So maybe there are 50 here and 10 here. Together, there are 60 electrons that are free. You cannot like distinguish between, oh, you came from thermal process, you came from donor. No, you cannot distinguish between these electrons. They're all free electrons, right? But they're created through different means. Okay, one other thing. So let's mark up the ones that we covered. We covered this donor electrons, we covered the acceptor holes, we covered the, by the way, I forgot to use that term here. These are called ionized acceptors, and these are called ionized donors because they have successfully given up electrons or created holes, and in doing so, they have ionized themselves. Making sense? As if they have made sacrifices and now they have medal. Right? You are ions. You are all ions. So they are ionized donors or acceptors. Okay? Or ionized impurities, in one word. Ionized impurities. However, remember, not all of them will always contribute. I'm taking back one comment that I just told you, as I kind of hinted at, right? If you use 1,000 donors, doesn't mean you'll be able to create 1,000 electrons. Many of them will not be activated, by the way. So in a fabrication process, there is a step that we take, which is impurity activation. We have to activate the donors and acceptors using some means. Not getting into the detail of that. Even then, you cannot guarantee that everybody will be activated. Okay? So you send 1,000 donors, maybe 900 will be activated, 100 will be just, they don't care. So there will be some unionized donors and unionized acceptors. So then, see, there is no charge there. Because as long as they don't participate, they don't give up any electron or take up any electron, they don't become ionized. They're just there. Just impurities for no reason. Am I making sense? Okay. So by the way, in a fabrication process, if you have a lot of these unionized donors and acceptors, would you think that that will be a good process, good fabrication process? If you are trying to be a good fab, would you appreciate having this? No, because that makes it difficult for you to count how many electrons you can accept. You are expecting to have 1,000,000 electrons, you get just 500,000. It's not gonna do much good for your devices, right? So you have to make sure whatever you do, you can activate as much as possible. Similarly, the other one. So process engineers, a lot of material science involved there. They do a lot of studies and research trying to make sure the best way to activate the donors. You don't want to use donors for no reason, because otherwise they will disrupt properties of the semiconductors. Okay, they're just impurities for no reason. Okay, now see, I mean, if we start marking things down, so this is also done, this is also done. It is easy for you to see what's not talked about so far. Intrinsic Fermi level, all of these have been discussed so far. You can clearly see what we haven't marked, right? One thing is this one. What's happening here? Can anybody explain what's going on here? Looks like a long process, but apparently these donor levels have given up electrons to the higher level, right? To the conduction band. Now they are all positive charges. They are all positive charge, but they're stuck. They cannot move around. Here, their acceptors, they have all taken up extra electrons from the valence band, which they actually don't need, honestly. They just made them like, I don't need another iPhone, but I just ended up buying because all of my friends bought one. Now I cannot get rid of it. What can I do? So what I'll try another friend who made a similar mistake like me. Maybe that friend gave up an iPhone because he was feeling, philanthropic, like, oh, everybody's giving up their iPhones. Okay, I'll give up my iPhone as well. But then he says, oh, I don't have any phone now. What should I do? And I made a mistake, buy an extra phone. So what I will do, if we meet each other, say, hey, I made a mistake taking this iPhone. You made a mistake giving up your iPhone. Here, take this iPhone. Anyways, the point is, this guy made a mistake in rhetoric sense by taking up an extra electron, which he didn't need. And these guys made a mistake by giving up their electrons, and now they're all ionized. Nobody wants to be ionized, honestly. So they can find a way to interact with each other and give each other electrons. For example, this acceptor can give an electron to this donor, which is now positive charge, and then they neutralize each other. So ionized donors and acceptors can then neutralize each other by interacting with each other eventually. Does that make sense? And I told you one really, really important thing, and I want you to have this in your mind all the time. Remember, these diagrams that you're looking at, these band diagrams, they don't show physical position of the donors and acceptors. Am I making sense? The donors and acceptors could be anywhere. They could be side by side. They could be farther out in the crystal. You don't know. All you're drawing in the y-axis, what do you have in the y-axis? Tell me. Energy. You're just showing. Maybe you and your friend could be side by side. You have more energy than your friend. That doesn't mean you're physically in a different place. Similarly, one atom could have more energy than the other. That's exactly what we're trying to represent here. So I'm preempting a question here. I'm expecting a question though. You might ask, why not all of them? I know it's getting very clumsy, so I'm gonna get rid of all of them. Why not all of these ionized donors interacting with all of these ionized acceptor and neutralizing everyone? Why is not that happening? Because not all of the acceptors and donors are side by side. You see my point? Maybe in a crystal format, these are say crystal. Just giving you a rough idea, essentially a 3D structure, right? So maybe say you have one acceptor here and say one acceptor here and a donor here and a donor here. Say for some reason they ended up being side by side and it's easy for them to interchange electrons. But it is difficult for these two atoms to interact and interchange electron, don't you think? So only in certain situations they will start interacting with each other and neutralize each other. Otherwise, they will not. Am I making sense? Basically, A and B and C. So AB and BC makes sense to basically BC could neutralize each other. But they will not because it's difficult for them to neutralize. They're so much further out from each other. Okay? So that's why not all of the donors and acceptors will neutralize each other, only a few. So that's what you see here with this interaction. Are you all good so far? And by the way, there are two other things that I didn't cover. Total electron concentration. What is the total? What do I mean by total electron concentration? So this is the total electron concentration. I kind of indirectly told you, but I didn't use the term. So you are creating some electrons as donor electrons. You're creating some electrons through thermal process. So together, they create the total electron concentration. I already told you, after there are electrons in the conduction band, there is no difference. They're all available for conduction. So the total electrons. And similarly, total hole concentration will be the sum of all this. All right. Okay. And there is some math, which I mean, these are the only two lines left to discuss. And I'm going to talk about it briefly. It's super simple. Look, a little bit like a math equation, but it's not. So imagine, what is the ionized donor number? Imagine you have used ND, number of donors. D stands for donor and N for number. Simple. Why am I telling you this simple stuff? Because these are standard. These will be used in all textbooks, all data sheets, everywhere. ND stands for number of donors. NA stands for number of acceptors. Okay, so simple. So imagine you have used ND number of donors, but only a few of them, say maybe in lowercase ND, didn't get activated. Okay, so they remained, they didn't even participate. They didn't give any electrons to the conduction band. So they are unionized donors. Okay, so you use that many donors, but a portion of them remain unionized. So how many ionized donors will you have? How many ionized donors will you have? Tell me. Total number of donors that you have used and the ones that didn't get ionized. If you subtract that out, the remainder would be the number of ionized donors. And that's what you, just to represent they're ionized, you use positive sign. Because donors, when they give up the electron, when you give up electron, you become positive. So similarly, they have given up electrons, so they have become positive. That's why Nd plus is Nd minus Nd. And you use the exact opposite notification to get the acceptor concentration. So Na is the number of acceptors that you have used. And since this is hole, remember, we typically represent electron with N and hole with P. Typically, that's how we do it. So we have Pa number of, unionized acceptors, say. So what is the number of ionized acceptor? It should be Na minus Pa. So similarly, I mean, just a different notation, but doesn't matter. It means the same thing. All right. So this image was taken from textbook, but otherwise I wouldn't even bother talking about this math. It doesn't matter. The concept matters. We are not doing any math here. But since it is here, I just might as well address it. So now, if you take all of this into consideration and do some math, and the math comes from a very simple concept, conservation of charge. In a material, in the end, you have the total number of charges should be conserved, right? You don't, if you create some charge, an opposite kind of charge will be created somewhere else and they will balance each other. So using this charge balance concept, and these steps are all provided in Newman's book, but you don't necessarily need to go through them if you don't want to. Eventually, you can calculate the total number of electrons and total number of holes in a compensated semiconductor. Does that make sense to you folks? You can calculate that, and these equations correlate the number of electrons with the donor number, acceptor number. ND stands for the number of donors you have used. Na stands for the number of acceptors you have used. Okay, and then same applies to the number of holes. Any problem so far? One thing that I didn't mention, there is also Ni. What is Ni? How many of you remember what Ni is? Intrinsic carrier concentration, meaning whenever you have an intrinsic material, no dopant at all, you still have number of electrons and number of holes created, right? And they're always created in pairs, as you remember. And the number of electrons and number of holes, I could write it here. N equals P equals Ni. That's the intrinsic carrier concentration. So do you guys remember one thing that I mentioned in the last lecture? There was a simple equation. How many of you remember this? I emphasized and I told you this is very important implication, right? So turns out even in compensated semiconductor, this equation will apply. So basically in any semiconductor, compensated or not, intrinsic or extrinsic, doesn't matter. The total number of electrons and holes, the product of them will be equals to Ni squared. And what does 0 represents? Do you remember that? Let me see. What does 0 represent? Anywhere if you see something with a 0 in semiconductor physics, it represents thermal equilibrium. So far, all we are doing, have you seen any voltage applied anywhere? Where are we applying a voltage? No. Magnetic field? No. Thermal gradient? No. Temperature is always there. And as I explained before, is there a delta theta somewhere? No. There is no difference in temperature. The entire material is at the same temperature, T. So that's why it's all thermal equilibrium so far. We'll quickly move out of thermal equilibrium and start looking at other things moving forward. Okay, so let's quickly use these equations. Okay, so we will use these equations in the next lecture. Sorry, I don't have the math problem here in this lecture, but in the next lecture, remember these equations, the origin of these equations, okay? We'll use these two equations to calculate, do a small math problem in the next lecture, which we will start with basically today. All right, so hold on for a few more minutes. So using that argument, and this is more like a revision of the discussion that we have had. Remember, these are taken from different books of the textbook. So I am covering the textbook chapter, essentially. So position of the Fermi level, I've already discussed this as part of the review process today, but I'm going to show you again. Conduction band, valence band. For N-type semiconductor, the Fermi level is closer to conduction band. For P-type semiconductor, Fermi level is closer to valence band. We have already discussed it. So done. This is done. Now, what does this diagram represent? All of these are taken from textbook. Now, let me explain that. Super simple. On your x-axis, just look at one version for now. Forget about the top. Forget about the top for now. So this is P-type. Don't look at the image now. Tell me, if I heavily dope a material with P-type dopant, will the Fermi level go closer to the valence band or move away from the valence band? Tell me. Closer to the valence. You know that, right? Look at the x-axis. This is the doping concentration for acceptor. So basically P-type doping. P-type doping, right? As you go to the right, it's increasing. So the heavier the doping is, the Fermi level is moving closer to this is valence band. Isn't that right? If the doping is heavy, the Fermi level will be closer to the valence band. That's what it shows. Exactly the opposite for N-type material. If the N-type doping is high, the Fermi level should go closer to the which band? Conduction band. So exactly, that's what you see here. As the doping concentration increases, the Fermi level, this is the Fermi level. This is the intrinsic level, but this is the actual Fermi level. The Fermi level is heading closer to the conduction band. Simple. So this diagram kind of correlates doping concentration with the relative position of Fermi level. We already know this. Any problems so far, folks? Okay. This is the last diagram. And by the way, here is what I did. By the way, I went to the textbook, took all the images that they used to explain different concepts, and have all of them in my slide. So basically, I've covered the textbook chapter. But you didn't realize because it's just one slide. Because honestly, it just takes a few words of explanation to go through all those chunks of text. But when you go through the chunk of text, at least that's how I felt as a student. I feel even more confused. What? Because there is too many jargons, too many technical, compensated, blah, blah, blah. Like too many, I forget by the time I get to the next page, what was this again? So this going back and forth, because remember, textbooks are not meant to be like pleasurable reading, right? It's like, okay, you read, maybe it could be, I don't know, good for sleeping sometimes. You could read textbooks before sleeping if you have sleeping problems. That's how it was for me. So I try to avoid text as much as possible because I guess the images are excellent. The images that this particular textbook uses, they're excellent. They could explain things quite nicely, but the related text could be a little bit cumbersome. Anyways, this is the last concept of the chapter that we are trying to finish up today. Fermi energy level for a system. Okay, and let me tell you a story. Few lectures down the line, we'll take an N-type semiconductor, we'll take a P-type semiconductor, we'll put them together, and that will explain the reason behind this slide. By the way, take an N-type semiconductor with a Fermi level closer to conduction map. You know that in an N-type semiconductor, Fermi level is closer to conduction map. We'll take a P-type semiconductor with Fermi level closer to the valence band. You have all told me that you heard about diode, which is a PN junction, basically PN junction diode. You take N-type, you take P-type, you connect them together. What happens to the Fermi level now? Will you have two Fermi level in the material? Tick and tack? No, like, will there be two different Fermi levels? Or what will happen to the Fermi level? This slide will answer the question, basically. Okay. Even before we head out and talk about PN junction diode, we are trying to understand what should happen in a PN junction diode, right? And that's exactly what this slide will explain. Imagine you have a system, system A, and you have a system, system B. Basically, you have two distinct, say, semiconductor samples, for example. And this one has a Fermi level EFA. This one has a Fermi level EFB. They have represented a really strange diagram. They could have just used, I mean, again, let me see. Okay, imagine you have Fermi level EFA, and let me just draw it here again in a simplistic way. EFB. Imagine we have the same baseline energy level, so they're drawn with respect to each other. Okay? So this is EFA, this is EFB. What happens when you put them together? So you had EFA, and now when you bring them in contact with each other, they become part of the same system because they can now interact with each other. Okay, so this was EFA and this was EFB. Question is, what will happen to the Fermi levels? Answer is, they will change in a way that they will all settle down to a specific unified Fermi level, EFAB. So basically, the Fermi level will match up to a level where it's uniform across the material. That's the answer. You cannot have two different Fermi levels in a common system. They will all come together in one level. And I have to add a note with a big asterisk, big asterisk. This is only true for thermal equilibrium. With external voltage, honestly, any device that you will ever learn about using semiconductors, I'm not talking about superconductors or other fancy stuff. Semiconductors, any semiconducting device that you'll ever learn about, BJT, diode, MOSFET, whatever, they will use just one trick. They will create asymmetry between Fermi levels in different zones of the device by applying external voltage. So in a non-equilibrium situation where you have external control with voltages, you perturb the Fermi level. You can change relative position of Fermi level, and you can make the device act in certain ways. You can control the properties of the device by changing the Fermi level. But if you let the device sit idle in an equilibrium condition, the Fermi level will come down and settle down. Am I making sense, folks? All of this will make a lot more sense, honestly, as we start talking about devices. And I'll correlate that with, remember, in that class I told you this will happen. And hopefully you'll be able to see that this is happening. Now, imagine two buckets of water. Okay, So it's kind of like one bucket filled up to this point, the other bucket filled up to this point. And the tip of the bucket is like Fermi level, by the way. So it's filled with electrons instead of water. And this is EFB. Now, what happens if I connect the two? Right? Somehow I connect these two buckets together. The moment you connect them, this water will realize there is a low energy path. Don't you think? Because it can minimize its potential energy and go to the other bucket. And eventually, where do you think they will stop? Given that they have the same, it doesn't look like it, but apparently they have the same surface area and whatnot. I'm just making everything uniform. Then they should stabilize at a situation where both water levels are exactly at the same level. Don't you think? That's our common sense. The same concept applies. Remember, it's all energy. Whether it's electrons or marbles or golf balls or footballs, doesn't matter. They're all trying to minimize energy from their own level. Okay? Doesn't matter what type of energy you're dealing with. Thermal energy, potential energy, kinetic energy, doesn't matter. So electrons, oh, by the way, the reason why it's confusing, the only thing that you need is this Fermi level. Why do we have this graph? Can anybody tell me what this graph is? Yes. So thank you so much. So typically, when we first talked about Fermi level, we talked about Fermi function, and the way you represent Fermi function in terms of this is energy. If this is Fermi level, this is Fermi function. Okay. The Fermi function is 1 below Fermi level, and it will be 0 above Fermi level. Remember that thing? Fermi function represents the probability of finding an electron, right? So below the Fermi level, all the energy levels will be filled with electrons. So that's why Fermi function is 1 here. But above Fermi level, at absolute 0 temperature, by the way, this is not absolute 0, that's why you have a gradual change. But at absolute 0, you have a sharp change. We have talked about all of this. So this is essentially Fermi function that they're drawing. Do you remember that? Okay. As you go above the Fermi energy, it becomes, we drew the same function over and over again, remember, in a different way. So if this is the energy axis, this is the Fermi function, imagine. And this is the Fermi energy. Below Fermi energy, the probability of an electron occupying an energy level is 100%. Above the Fermi energy, it was 0. Do you remember that argument? And then I told you these are all for absolute 0 temperature. But if you have non-zero temperature, then there will be a gradual shift through the midpoint, and that point was half. And we talked about all of this. And this is, I think, in my opinion, this is much easier to understand view. But in textbook, they just flip it around. Like they have the Fermi energy in the y-axis and energy in the x-axis. That's why the graph basically just flips. And that's what you see here in the textbook. Simple Fermi function. You can just ignore it. Just imagine that you have a Fermi level, you have another Fermi level, you're bringing them together, they'll interact and they will come to a common level. And here's how, instead of buckets of water, think of energy levels that are being filled with electrons. I don't know if this is visible enough, but the textbook uses dark gray to show all these energy levels are filled with electrons. You see that blue dots, they're electrons. So they have filled up the energy levels up to this point. Why up to this point? Because this is the Fermi level. So all the energy levels up to the Fermi level should be filled. And all the energy levels above Fermi level should be empty at absolute 0 temperature. Does that make sense to you? So this is what this diagram shows. Similarly, here, all the energy levels below the Fermi level are filled and the above are empty. But when you bring them together, when you bring these two systems together, these electrons, notice, these electrons are basically at higher energy compared to the energy levels that are available here. So when these materials are separate, there is no way for the electrons to go and take up those energy states because they are not part of the system. So when they are brought together, now the electrons can possibly move over to the other energy levels instead of staying here. Oh, I'm not happy here. I'm just going to go to the other material and find my place. And that's exactly what they're going to do. Exactly what water does. See, The fundamental reason is the same: minimize energy. Whatever water does, electron does the same thing. It goes to the other energy level, to the other side of the material, minimizes energy, and now the Fermi level comes down and it's flat, straight and flat. Does that make sense to all of you? That's exactly what will happen to any material. Okay, BJT. How many of you have heard about bipolar junction transistor? There are two types, NPN, PNP. Okay, you have N-type semiconductor, P-type semiconductor, N-type semiconductor. Three different kinds of semiconductor. At thermal equilibrium, they have one flat Fermi level. That's where we start. And then we change them with respect to each other. Okay, meaning like Fermi level in this zone versus the other zone versus the other zone. We take them up or down by applying specific voltages. And that's what controls the material, controls the device functions. So this is how critical for you to understand. You know, if you don't understand the Fermi level, you will probably say, okay, this is how it works, but you'll never really understand what goes on. You know, the problem with superficial understanding, because I could just teach you this is how diode works. Turn on voltage, it turns on after a certain voltage, gives you IV, like exponential stuff. And you're doing that, by the way, part of your lab, I hope, right? You're testing diodes, you're designing circuits with diode. This is all good. The problem occurs at point of inflection, like whenever something changes. Now, I don't mean inflection, like point of inflection where something dramatically changes. So you are at a age where things are changing in semiconductors. If you don't understand the fundamental way things were designed from ground up, you'll never be able to redesign anything. You'll never know how we arrived at this conclusion. So you'll keep reinventing the same thing over and over again. Am I making sense? So you need to understand the fundamental reason behind the device principles, and then all of these will be relevant by the time you get to your actual career. So you have to do and make new designs. So by the way, this lecture is done. So we are moving over to the next one. I already uploaded the slides. I hope one thing that I keep doing, I don't know if you could see it. I haven't checked whether I made it public. If not, I'm sorry. I'll go and make it public again. It is available. Oh, thank you. Thank you. So I feel better. All right. So this one will take us to a different zone. This is an interface lecture. What do I mean by interface lecture? So far we talked about thermal equilibrium. In the next few lectures, we'll talk about inequilibrium, obviously, right? As you can imagine. Now we'll start providing external stimuli, voltages and other stuff. In between, we are learning to understand the phenomena of carrier transport. So basically, how will the carriers, like when I say carrier, I talk about electrons and holes, both. That's why, not electron transport, not hole transport, carrier transport, because they're carriers. So we'll try to understand the different ways the carriers can move around in a system, in a semiconductor. And after that, we'll start talking about inequilibrium. So it's going to be a much smaller lecture than the other ones. So we'll get started. These are all taken from textbook, but I'm gonna I will definitely not read any of them, but please read them at home. I'm going to hop through these equations and explain how they come into being. So there are two fundamental ways how electric current flows through a material: drift current and diffusion current. Okay, turns out all semiconductor devices that you could describe, at least until the last decade, okay, even the modern day devices, they deal with drift current and diffusion current. So this is how critical these simple lectures are. Okay, so if you understand how drift current comes into being, how to calculate it, how to represent it, great. You understand all the device basics with drift component, and then there will be diffusion component. In the most advanced devices, there is a different transport component called ballistic transport. That's a very different thing. It doesn't care about drift or diffusion, just as the name suggests, ballistic, right? It's like, okay, we'll talk about it at some point. Maybe I'll try to give you a high level overview of what that is. But for the most part, most semiconductor devices just deal with two components, drift and diffusion. So we're looking at one of them. What is drift? When a charged particle is kicked around by electric field, that's drift, basically. Like, that's drift. Although the name might have raised some hope in terms of drifting cars and whatnot. I don't know if you have watched Tokyo Drift, but but it's not really that one. It's not really as exciting as the real drift. So it basically means there is a certain direction that the charge will go, and the direction will be controlled by electric field. So there has to be an external electric field. Only then there will be a drift current. So a drift current is discussed or described as charge density times velocity. Okay. And by the way, remember, this is current density. So typically we start with current density. Current density means current times unit area, current per unit area. Okay. All right. And I will tell you the reason why we talk about current density. How many of you have heard about Ohm's law? All of you, V equals IR, right? We all know this. You know, it doesn't really apply to most materials. It's a very, simplified law, but the real law should be, so you see here the voltage equals current times resistance. Instead of current, you should use current density. All right. Instead of voltage, you should use electric field. Instead of resistance, by the way, if you take the resistance to the other side, 1 over resistance is conductance. Okay. So conductance is often basically is a more fundamental property that the material provides. And instead of conductance, we should treat conductivity. So sigma J equals sigma E is a more fundamental version of Ohm's law that we should care about. So that's why, again, I'm not getting into the reasoning behind these and that. Maybe this is covered in like high school, not high school, maybe first year physics mostly. Why this one is not more appropriate, this one is more appropriate, vice versa. But the point is, that's the reason why we are looking at current density instead of current directly. Okay, current density. So current density for drift or drift current density is related to the charge density and velocity. So imagine in a certain space, you have a density of charge. It could be negative charge, it could be positive charge. So there is a density. How do we measure the density? Coulomb per, typically, depending on whether you're measuring 3D or 2D density, we could measure it in Coulomb per centimeter squared or Coulomb per centimeter cube. But you will see, for the most part, we often measure it in Coulomb per centimeter square. We try to, abstract out the other dimension. Anyways, I don't want to confuse you too much. We'll do a math, and then it will be clear. So we'll do a math here, and we'll talk about all these, units and why these units are used, why centimeter squared is used in a second. But for the time being, just treat it like a density. You have a bunch of charge in a unit volume or unit area. That's charge density. And that charge density is moving around a certain velocity, at a certain velocity, okay? That's V. This is the drift current amount. Are you guys with me so far? Okay. Now, imagine if I tell you that you have a given number of charge, n number of charges, and every one of them has q amount of charge in them. So you have charged particles, n number of them, and every one of them has q charge in it. What is the total charge? What is the total charge? Q times n. Simple. Every particle has q charge, and you have n numbers of particles. The total charge in that assembly would be qn. As simple as that. Imagine, we'll start with holes, by the way. Imagine in a semiconductor, you have p numbers of holes. That's why we use p to represent holes. P numbers of holes. How much charge with each of these holes will have? Can anybody tell me? So basically, hole is nothing but absence of electron. If an electron has E charge, a hole will also have the same amount of charge, just positive. So I can say, if there are p number of holes in a semiconductor, each one of them has E charge, the total charge in the assembly would be EP. And that's what you see here. You might be wondering, hey, this was supposed to be charge density. Why are you calculating charge? Because I didn't tell you, P is not the number of holes. It's number of holes per unit volume. Okay, that's what I don't know if you remember that. When we calculated N and P and using some equation, don't worry, I'll upload a second homework and you'll do some maths, and hopefully this will be brushed up much better. And you'll see, oh, I see. This is how you calculate N. N and P is always represented in terms of unit volume. Because otherwise, how will you know how much electron is there in the material? Because you haven't defined the size of the material, right? we always calculate them per unit volume, so that you could have a material of this size or that size, so it doesn't matter, right? So that's what the reason is, because P is already per unit volume. So what you get here is charge density, not charge density. And the drift velocity remains the same. By the way, drift velocity has an interesting property. Drift velocity is when you imagine you have a charged particle and you apply an electric field somewhere, and that electric field is kicking around this charged particle and pushing it in a certain direction. So it's drifting. Okay? So you can easily calculate the velocity by looking at how much distance is traveled in a given time. And you can calculate the drift velocity approximately. It's simple to say if the particle is free. But remember, in a semiconductor, in any material, you don't have an open free space. The electrons that are flowing, even driven by electric field, they basically get kicked around. Right? So if there are atoms here, the electrons will be, scattered, and they will be repelled by different crystal atoms, different atoms in the crystal. Therefore, they will not be as simple as d over t, right? Because they are not just flowing from point A to point B. There are a lot of interactions in the middle. Does that make sense, folks? But despite that reason, we could easily calculate experimentally a velocity, an average velocity, and turns out this velocity, let me just get back to this one. Experimentally, we see that the velocity, drift velocity, is proportional to the electric field, because the more electric field you apply, the more velocity you see. So you see almost like a linear relationship. More electric field, more velocity. Simple, linear. Okay, and if I tell you that this is y versus x graph, and this is a straight line, can you tell me the equation for this straight line from high school? Y equals mx. If it goes through the origin, y equals mx. Simple. So we could represent it as a straight line, but if we just write y equals mx, it doesn't look as fancy. So we have to come up with a constant. A constant, if the constant is taken from some sort of Greek alphabet, it looks even more fancy, right? So instead of ABC, we decided to use mu. So instead of y equals mx, we decided to use, what is y here? Velocity. What is x here? Electric field. And instead of m, we just decided to go fancy and write mu. V equals mu e. That's all. So that's what you see here. V equals mu e. Why do we use P? To represent it's for holes. Anything with P represents holes, and anything with N represents electrons. In my opinion, it's a little bit confusing. They could have used H to represent hole. It doesn't matter. It's not my my call, right? So they represent holes with P because that's a positively charged particle. That's why. And N with electrons. Okay. Now, all right. Oh, by the way, and I'm explaining this reasoning because this will keep coming up over in all data sheets, all textbook, they use the same notations. Okay. So D stands for drift velocity for holes. You can only imagine what will be the drift velocity for electron. V, D, N. Not E, not electron E, right? N, negative. That's how things are. VD, N, drift velocity for electron. VDP, drift velocity for holes. Okay, now putting that thing here, you see drift velocity equation for holes, which turns out to be the charge of electron times mu p, which is a constant. Remember, this is a constant that we could measure experimentally. I mean, if you do some experiment, imagine you go to the lab, you test. If I apply E1 amount of electric field, you get V1 as voltage. If you apply E2 electric field, you get V2 as velocity. E3 electric field, you get V3 as velocity. You plot them, and you see there is a straight line. You can easily calculate mu from this straight line by taking tan theta, right? Am I making any sense, folks? All right. So experimentally, you can easily calculate mu and P, obviously. So apparently, the drift velocity is a function of the electric field you apply, the number of holes available in the system. If you have more number of holes in a system, there will be more current or current density, mu and E. Simple. One more thing that I want to highlight, the same applies to electrons. You could just use the same argument and do that to electrons. The only things that will change, instead of mu P, you have mu N now. which is electron. Instead of P, you have number of electrons, N. Everything else remains the same. But there will be some discussions about the sign, positive sign and negative sign. And I'm going to explain that in a second without going through this confusing stuff. Okay, let me explain. Imagine in a system, you have some electron and you have some holes. Let me just represent holes with this H plus. And you are applying an electric field. Okay, the electric field will have a positive and negative direction. So imagine you have somehow an electric field like this. Say, are you good so far? You have the positive terminal here and negative terminal here. Where will the electrons try to go? Towards the positive terminal, don't you think? Negative charges like positive terminals. Are you guys all with me so far? How many of you remember that there was a convention hundreds of years ago when people started using electricity? The convention is wherever electrons flow, the direction of current flow will be the opposite. Do you remember that from your high school? So wherever we show that current is flowing in this direction, that means electron is actually flowing in the other direction, right? It came into being like hundreds of years, 100 years ago, like actually in early 1900s, maybe even before that. So we never changed it. So using that, convention, if the electrons flow in this direction because they love positive terminal, where will be the direction of current? Can anybody tell me? Yes, thank you. Your point. Yes, electron current will be this direction. Current due to the electron flow will be this direction. Okay. And by the way, this is only for electron. If a positive charge flow, and I hope you must have seen that in batteries, right? When you see batteries in chemistry, wherever the positive charges go, current goes in that direction. Wherever the negative charges go, current flows in the other direction. That's the convention. Okay. So holes will not go towards the positive terminal. They will actually go towards the negative terminal because they are positive charges. But since they are positive charge, that's where the current will also flow. So when you apply an electric field in a system that has both electrons and holes, they will basically work with each other. Electrons and holes will both contribute in current flow. They will not work against each other. They will flow in the right direction. Does that make sense to you guys? Remember compensated semiconductor where you had both electrons and holes? Doesn't matter. You're creating carriers. Look at the bright side. Doesn't matter whether it's electrons or holes. You're creating carriers. When you apply an electric field, they will both work with each other and contribute to current, which is a good news, don't you think? Does that make sense? Okay. In an intrinsic semiconductor, remember, electron and hole pairs were generating by the same number. You have as many electrons as holes. You might think, oh, they will just cancel each other. But when you apply an electric field, both of them will take part in conduction. So they're useful, don't you think? So if you have a material with really heavy intrinsic carrier concentration, very good because they can both lead to drift current. There will be a catch. Obviously, there is always a catch, right? And we'll see what happens to diffusion in a second. There is another component of current, and hopefully that will be clear. But considering all of this, what I just explained to you, like direction of current is considered opposite of electron flow. All of these negative and negative discussions will be mentioned here. Let me talk about it. Okay, so when we try to calculate the direction of current, what is the concentration of charge here? This is the concentration of electron in general. So when we consider that a chunk of electron is moving in one direction, we have to use a negative sign to represent the direction of current. That's why the negative sign here. Okay, so the negative sign comes because of the flow of electron instead of flow of holes. Okay, apparently they will arrive at the same conclusion. I mean, the way I just explained. Okay, but I'm still gonna go through them quite superficially to show you why they have two negative signs here. And the other one is, using the velocity versus electric field, since the electrons move in the opposite direction of holes. So imagine if you are conducting the experiment of velocity versus electric field with holes and electrons. Wherever the holes go, electrons will go in the other direction. So their velocity has a direction, as you know, it's a vector. So the direction of velocity will be opposite to that of holes. Don't you think? Right? So that's why they used a negative sign here as well. So these two negatives cancel each other and you end up with a positive sign. Apparently, it doesn't matter. You don't have to go through all of this. You just remember that, okay, electrons move in this direction, holes move in that direction. So apparently the current will move in the same direction. So they will add up. What is the end point? The end point is these two components will add up. That's where the textbook comes into eventually. So these two components will add up, and the total drift current component for electrons and holes is this. Are you guys all with me so far? Do you recognize these equations? Individually, you have this one, you have the other one. If you add them together, electric field is common, charge is common, these two will be separate. Simple. Okay, as simple as that. Let's move to the next slide and talk about a simple math problem. And this is where as I promised, we'll also use the compensated semiconductor equation that we saw in the last lecture. Okay, consider a gallium arsenide sample. And all of these are clue, by the way. When you see gallium arsenide, there will be a table given, and you go to gallium arsenide table and find out mu and mu p. And I forgot to mention, by the way, in the previous slide, but although I showed you, this mu is experimentally measured. It is a constant. We have to give it a name, right? Without a name, what should I refer it with? Should I just keep saying it mu? And it's called mobility. Okay, mobility of electrons, mobility of holes, because it is related to how fast the velocity is. So people decided to call it mobility. So you experimentally measured it with velocity versus electric field. You can easily measure the angle that comes up from the straight line, and that angle is your, like, if you take the tangent of that angle, you have mobility. And if you repeat it for electron, you have mobility for electron. If you do it for holes, you get mobility for holes. Simple. Any problems so far? And people have done this for almost all materials that you can think of. Okay, so you don't have to worry about any of this. This chart goes on, like, for all the materials that you can care about. You come up with a new material, like an alloy, say aluminum, gallium arsenide, blah 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 blah. Okay, take it to the lab, do the same experiment, measure mu n and mu p, add to the table, done. Okay, that's what material scientists do. But for our purposes, gallium arsenide, we know the mu n and mu p. Okay, at 300 Kelvin temperature with doping concentrations, something and something. So they have given us both type of doping concentration, acceptor and donor. They cheated it, by the way, in a way that one of them is 0. So basically, this is not useful, but practically both of them will have some number. Okay, calculate the drift current density if the applied electric field is this much. So I'll start with what we need to calculate. We need to calculate the drift current density. We just saw that this is the equation. So you need to calculate. I'll show you what you need to calculate, but you know the electric field. Just put that in. You know the charge of electron. Put that in. You know mu n and mu p because they have told you the material, gallium arsenide. So you can easily plug mu n and mu p from the table. What do you know? What do you need to calculate now? You need n and p. Number of electrons available in the system, number of holes available in the system. Does that make sense? Okay. So for that, let's use this equation that allows you to calculate the number of electrons. And by the way, there is another equation. Let me just, in 30 seconds, let me just go back to the previous slide. I want you to see the actual picture. See, there were two equations, one for electrons, one for holes. You could use both of them and plug in Nd and Na and Ni, and you get N and P. Simple. Don't you think? Does it make sense? Okay. So they just, in the textbook, they just made it even simpler by making one of them 0, which wasn't really necessary. Anyways, so you use this equation, plug in Na and Nd, and Ni is also available not in this chart. There is another chart with intrinsic carrier concentration. You get N, and you do the same, get P. But there is one trick that they did, which I liked, by the way. You don't necessarily need to calculate N and P with those cumbersome equation. If you calculate N, remember I told you, N P product will always be Ni squared. So if you calculate N, you could just use this equation to calculate the other one. In fact, that's how the equations were derived, by the way. Okay, so there you go. So let's stop here, and just to let you know, this V versus E diagram that I've drawn so far, there is a mistake. There is a deliberate mistake. And we'll talk about that mistake And the mistake is it will not go on like this forever. It will saturate. And we'll talk about that saturation case in the next class. Okay. Thank you.